In this presentation, I'm going to show you how to conduct a two-sided hypothesis test when we know what the variance is. I'm going to do this by working through an example. So let's say that we have a machine, and this machine allocates paper to different ream sizes. So let's say it's printer paper, and what it does is it allocates 100 pieces of paper to a single ream. And what we want to ultimately determine is whether or not this machine is producing parts correctly. And so what we need to do is we need to put this into terms of hypotheses so that we can actually go in and answer this question. So one of the things we know is that 100 pieces approximately weighs 0.45 kilograms. So when we construct our hypothesis test, we want to use that knowing that this ream is supposed to weigh 0.45 kilograms. So our first hypothesis, which is the null hypothesis, states that the mean, so the mean of our samples that we collect, so the data that we collect, is equal to 0.40 or 0.45 kilograms. And our alternative hypothesis basically states that it's not equal to 45 kilograms, to 0.45 kilograms. So ultimately we have two hypotheses. We have a hypothesis that says it is working and a hypothesis that says it isn't working. So this is a two-sided hypothesis test because we're trying to determine if the mean is equal to or not equal to something. So it's two-sided. So in order to do this, we have a fancy schmancy process to follow. So the process for conducting our hypothesis test is first to define the null hypothesis, or H0, and the alternative hypothesis, H1. And we've already done that. Remember, it's mu is equal to 0.45, or mu is not equal to 0.45. So the next thing we need to do is we actually need to go and compute x bar. And remember, x bar is our mean, our standard mean. So to do that, we're actually going to pull up Excel. So you can see in Excel that I've already gone in and I've put in the values that we've collected for our sample. And in our case, we had a sample size of 15. So we took 15 paper reams and we weighed them, and these are the different weights that we collected. So I'll even put this into kilograms. We have a standard deviation of 0.01, which we know based off of the variance. So if you recall, in this example specifically, we know the variance. So the thing that we need to do first, again, after we've identified the null hypothesis and the alternative hypotheses, is we need to calculate x bar. And to calculate x bar, it's essentially the average of these. Hit enter. And we've calculated x bar. Now that we know what x bar is, the next thing we need to do is we need to go in and we need to calculate Z0. And Z0 is given by the equation Z is equal to x bar minus mu naught divided by sigma, which is our standard deviation, divided by our sample size n. So let's go and compute that in Excel. So Z0 is equal to x bar, so that's this, minus mu naught which we've defined here based off of our null hypothesis, divided by the standard deviation, which is 0.01, times the square root, divided by the square root of our sample size, n. So close up our parentheses, and we get a z-naught of 1.299. So the next thing we need to do now is we need to go in and compute p, or a probability. And we're going to do this first, and then we'll do finding z at alpha divided by 2. The probability is equal to 2 times 1 minus the probability of z-naught less than or equal to the absolute value, which I can actually represent with lines here, of z-naught. So let's compute that in Excel. So in Excel, to calculate probability, again, it's 2 times 1 minus the probability, and in this case we're going to use the norm S-dist, because again we're using a z-value, so our standard, we standardized it, times the abs of our z-naught, parentheses in, and we get a p-value of 0.019. So when hypothesis testing, some of you may have seen this, but you, as a statistician or an engineer, scientist, you essentially go in and choose an alpha value, and that alpha value tells you sort of the desired probability that we need to make a type 1 error. So basically, we're going to choose an alpha value of 0.1, and that says that a probability that is greater than 0.1 is is likely to lead us to a type 1 error. So in that case, by comparing the probability we have here with this alpha probability, we see that the probability is actually greater than this alpha value. And so we are going to have that type 1 error, so we don't really want that. So what we're going to do is we're actually going to reject the null in this case because this p-value is greater than alpha. And in that case, basically we're saying that the machine is not correctly distributing or counting the paper for its reams. But there's another way, and some would say that this is more accurate, to actually go in and test that sort of to determine whether or not we want to reject or accept the null hypothesis, and that's by doing this z alpha over 2 value. So to compute the z alpha over 2 value, we essentially need to compute what alpha over 2 is, and then compare our computed z-naught, which we computed up here, with our z-value for alpha over 2 to see if the z-naught falls in this critical region, and if it does, then we reject the null. So let's go and do that. So in our case, to calculate that z-value for alpha over 2, what we need to do is we need to use the norm S inverse function, because we're trying to get a z-value. And our probability, because our probability is based off of this alpha, is going to be 1 minus, in our case, alpha over 2. And we get a z alpha value of 1.645. In this case, you can see that our z value is greater than our z alpha value over 2 is greater than our z naught value, so we can assume that we can accept the null hypothesis because essentially we're determining that our z naught doesn't fall into critical region. But let's see what that actually looks like so that you can actually see what I'm talking about when I talk about a critical region. In the case of the first approach, we were essentially trying to find the probability where something was more extreme than z naught on both sides. So we found a z naught value, and we wanted to find what that probability was so that we can display here, such that it was less than alpha. Because basically what we want is we want this probability to be so small that it in effect means that we've limited our type 1 error. The probability was actually greater than alpha, and as a result we rejected the null, which is just h naught. In our second approach, we use the z of alpha over 2, and again we had a graph here where this was our z value, negative z value, and in this case our z of alpha over 2 was here because it was greater than our z naught value, so that meant that our critical region moved over here, and because our z naught value wasn't in that critical region, we can accept a null. So I hope you have a better understanding of what we did today with our two-sided hypothesis test on the mean when we know what the variance is. Thanks.